right? The ligand metal interaction which take place in a vessel, it only happen when oxygen is oxygen, not O plus. The moment it become O plus, it will not bind with the metal. Then there is an aggregation of the metal itself starts, which will give you a different product. Similarly, when you increase the pH, the water is not remain water, it will is OH minus. OH minus. Now OH minus work as a ligand in place of water. OH minus is a better ligand than the water, right? So in such cases, the product will form is different. Okay. So what will happen? The interaction, for example, I am talking about HSE principle, soft and hard interaction. The moment you change this scenario, a different intermediate will form, and this intermediate will give a different material. That's the role of the pH. It's like you take a sheet, you take a chalk and write on the board. That's what it is. So you are removing layer by layer. That's what it is. So when you use the sandal, rub the sandal and put on the head, that's what the exact process. You might have heard about it that in the villages people are using neem bark when they have some pimples. Have you heard about it? That's exactly happening. They rub it and make a fine layer. This fine layer have the antibacterial property in two ways. It's nanomaterial in the size, as well as it's antibacterial by nature. Okay, so using the this sandals and then number of things, people are using paintings, single layer. So this is the process that. So the graphene was discovered like that, from out of the graphene oxide. The single layers are etching out, and still people are practicing this. But this particular process is you cannot transfer to the industry, because when I talk about something, I am mostly focusing that if the process is transferable to industry. If it is not, I don't think that we have to practice for a long time. So if the industry viable process is the one which we need to discuss, so that's the reason this liquid has come from the physical.
The solid state with the high pressure, low temperature is possible.
Solid, how you will do? See, solid is a diffusion control reaction. So for diffusion you require high temperature. So that's the reason that industry don't like that solid reactions. So when there is a diffusion control reaction, the high temperature is needed. That's why it cannot be possible at low temperature.
Sir, is it necessary that the nature of solvent has to be aligned with the metal?
See, there are two things. Okay, for example, if you want to travel from one place to another place, you have two targets: how fast you want to reach, okay, or where you want to reach. There are two things. Okay, I said I want to reach this place, I don't care about time. Then you can take the option of any vehicle. But if you want to reach fast, your options are there. Okay, so similar in the material, which exact material you want to make, that will decide your reaction conditions.
For example, TiO2 is a hard material.
Ti plus 4 is hard.
TiO2.
No, TiO2 don't have any such nature. Titanium plus 4 is hard, and oxygen is also hard. That's the reason TiO2 is very strong and very stable material.
For TiO2, which kind of solvent?
Water. What is the best one? Because this TiO2 mostly prepared by the hydrothermal processes.
So size of the particles you can control by chemical process.
You can in the which process you are talking about? Hydrothermal?
Any synthesis process.
No, any synthesis. Each synthesis has a different linings. Okay, if you can tell the particular process, I can throw some light on. So if you're talking about hydrothermal, yes. If you're talking hydrothermal, yes. You raise the temperature, the pressure will increase, and the moment it will go supercritical, the particle size will be small. you come down the temperature, and then the particle size become bigger. This is a proved method.
So if there is no additive during the hydrothermal reaction, what will happen?
Pardon me?
So if there is no additive during the hydrothermal reaction, what will happen?
The most stable nanoparticle will form. Most stable. Thermodynamically most stable will form. If you are not providing any direction, for example, if you are going from A place to B and there is a straight road, you definitely reach there, but there is a bifurcation of the road in between. There is a chance that you will lose somewhere else. The bifurcation of road is what the additive.
Hydrothermal, basically when we are adding some additive, there is a at that temperature the nucleation of particles start. Okay, so we get some nanoparticle at that temperature. Now we have to get those particles. So we'll cool down the solution, filter it off and get the particles. So during cooling down, that size will be same as at the nucleation time?
See, once the nucleation starts, the size will not vary. Because it's a nucleation. You are seeding already. Once it's seeded, then it will follow the process. Like when you have some supersaturated solution and you put a seed of a crystal, the all crystal morphology will follow that. Okay, it's like they basically follow the simple principle of of the chemistry. Because crystals are well latticed. The lattice energy is high, so they will follow the high energetic process with thermodynamically more stable.
So in gaseous state, so which gases we can use?
See, the gaseous stage normally when you talk of the when you take, it's not the, I'm talking about the gas. You have to raise the temperature of the material to convert into the gas, and then it decomposes. For example, if you take like nickel COD complex, for example, COD is organic compound. At high temperature, decomposes, give the nickel 0. So you will get the nickel 0 particles. But for that purpose, you require a large voluminous, and there is safety issues. There are safety issues. That's the reason industry don't like it. Gaseous. Any other question, please?
Thank Dr. Sharma for giving a wonderful talk. And now we will have a group photograph. Okay?
Good photograph?
Group photograph.
Okay.
Before we go for the next lecture.